In this lecture, we will learn about eigenvalue and eigenvector problems. In these problems, we are given a matrix A, which in general is an n by n matrix with n rows and n columns. X is an n by 1 matrix, which we can call a column matrix or just a vector. And in these problems, this vector x will be known as eigenvector, and lambda is a scalar and it will be known as eigenvalue. And the eigenvalue problem is represented by equation ax equals to lambda x. Now there is a long method to solve this equation and find eigenvectors x and eigenvalues lambda, but in this lecture we will only focus on shortcut method, find or determine eigenvalues and eigenvectors. This shortcut method is based on three main properties of eigenvalues and eigenvectors. The first property of eigenvalues and eigenvectors is derived from the eigenvalue problem itself. Before we look into that property, let's understand one concept. In general, if we multiply a matrix with a vector, then both the magnitude and the direction of the vector will change. For example, if A is a matrix of size n by n, y is a vector of size n by 1, then the product of A and y gives me z, which will have size n by 1. In general, the magnitude of z will not be equal to magnitude of y, and the direction of z also will not be equal to direction of y. That is, when we multiply a vector with a matrix, both the magnitude as well as direction will change in general. However, if we multiply a vector with a scalar, then only the magnitude of the vector will change. For example, if I multiply y with scalar k, then I get z. Then the direction of vector z will be same as direction of y, or at the most the direction will reverse if the multiplying scalar is negative, and the magnitude of z will become equals to absolute value of k into magnitude of y. And here we are taking absolute value here because the magnitude of a vector cannot be negative, and if k is negative, then this absolute value operation will make that positive. So here we can say that upon scalar multiplication, the vector y is just scaled by factor absolute value of k. So scalar multiplication only scales the vector without any rotation. Now if we look at the eigenvalue problem equation, it says that if we multiply the matrix A with vector x, that is equals to scalar multiplication of that vector x. So if x is an eigenvector of matrix A, then matrix multiplication of x with A is equals to vector multiplication of x with lambda. That means the matrix multiplication in the case of eigenvector is equivalent to scalar multiplication, and the scaling factor lambda is known as the eigenvalue of A corresponding to the eigenvector x. So this is the first property of eigenvalues and eigenvector. Then the other two properties make use of all the eigenvalues of matrix A. So if lambda 1, lambda 2, lambda n are all the eigenvalues of matrix A, then second property says that sum of all the eigenvalues is equals to trace of matrix A, and trace of matrix A is nothing but sum of all the diagonal elements of the matrix A. So here trace of matrix A will be sum of all the diagonal elements, that is A11 plus A22 plus A33 plus dot 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 plus ANN. And the third property says that product of all the eigenvalues of the matrix A will be equals to determinant of matrix A.